In this video, we're going to talk about the concepts of effusion and diffusion, which are very similar and governed by a similar equation. So effusion is where you have a mixture of gases, and I'm showing it as filled in circles and not filled in circles, in a container, but there's a hole in the container, and the gases escape into a vacuum where there are no molecules whatsoever. So that is effusion. So gases escape out a hole into a vacuum. And a vacuum is simply a place where there are no molecules. Diffusion is very similar, except that you picture it this way. You start with the gas molecules separated. You have one type which is filled in circles, one type which is not filled in circles, and they're separated by some barrier. If you remove the barrier, then those gases will mix. And the rate at which they mix is diffusion. The process of mixing is diffusion. And they mix into another gas rather than into a vacuum where they go out where there's no molecules whatsoever. So diffusion is where gases mix into another gas. And this process, the diffusion process, is slower than effusion. Okay, this process is faster because they, well, think about it. Why would it be faster? Why would this one be slower? And the reason is that these molecules can hit like the filled-in circles might hit another molecule and bounce back. So they aren't going to move into the other space as fast as these will move in because there's nothing to collide with. Okay, so it's slower than effusion. And that's because there's nothing to collide with in a vacuum. But both processes are covered by Graham's law, where you say that the rate of diffusion or effusion is proportional to 1 over the square root of the mass. Okay, so since it's a proportionality, the proportionality is different for effusion and diffusion. Effusion is faster, diffusion is slower, but they're both proportional to 1 over the mass, the square root of the mass. Okay, which basically tells you that lighter gases will effuse or diffuse more quickly. Okay, it's inversely proportional to the square root. All right, so we can actually, since it's just a proportionality, what we can do is compare two different gases, since we have in both these cases the filled-in circles and the not filled-in circles, and we can compare the rates of two different types of gases. And we'll call the two gases A and B. Okay, so I'll mark this is gas A, and this is gas B. It's totally arbitrary. So if we want to talk about a comparison for either effusion or diffusion, we can say that the rate for A, molecule A, whether it's effusion or diffusion, divided by the rate for B is going to equal, and we can use, since it's inversely proportional to the mass, we can use a big square root and put the mass of A on the bottom and the mass of B on the top. Okay, because they're inversely proportional. So the B's are across from each other, the A's are across from each other, and they're both under the square root. And so this is our expression of Graham's law, which covers both. So again, the rate of A and B effusing would be faster, but the ratio of the rates of A and B effusing are the same as for diffusion. All right, let's do some examples. Let's say we have a mixture of three noble gases, argon, krypton, and neon, and they're placed in a container that has a small hole. Rank the relative effusion rates, and then the second question, what's the ratio of the rates for argon and neon? So what are the relative effusion rates? Let's rank them. Which one's going to be faster? Look at their molar masses. Okay, the heaviest one is krypton. The lightest one is neon, if you look at the periodic table. So which one is going to go faster? The rate is inversely proportional to the square root of the molar mass, so a heavier substance will effuse out more slowly, and a light substance will effuse out more quickly. So the relative rates are going to be krypton is the slowest, followed by argon, followed by neon. And that's a problem. So we'll erase this, followed by neon. Okay, so that's the relative rates, but now the second question, what's the actual ratio of the rates for argon and neon? Okay, so the rate for argon divided by the rate for neon is going to equal the square root of the mass of neon divided by the mass of argon. Remember, they're across each other. Neon goes bottom to top and argon goes top to bottom. Okay, so what are the molar masses of argon and neon? Argon is about 40, 39.95, and neon is about 20, 20.18. You don't need to put in units because they will cancel. They're both the same thing. And when you do the square root, you get 0.7107. You could also do the rate upside down. You could do neon on top and argon on the bottom. So you could do 1 over this number. And that's probably often preferable to do the other way around. To do the lighter one on top, because then the number will be bigger than 0. And that will be 1.407. So the rate of neon effusing is about 1.5, a little less than 1.5 times the rate of argon effusing out of that container. All right, here's another problem for you to try. And so you should stop the video and work on that yourself and then check my answer. But this is 2 noble gases effusing out of a hole. The ratio of the rates, now you're given the ratio. If one gas is helium, what's the other gas? So try that problem. All right, so what do? We have a number for the ratio of the rates. So the rate of something over the rate of something else is equal to 3.16. Now that number is obviously greater than 1, which means that the lighter molecule is going to be on top. It's going to be rate A, the lighter molecule. The heavier one will be rate B on the bottom. So since they're both noble gases, and helium is the lightest noble gas, we know that the one on top has got to be helium. Okay, so we know that the rate of helium to the rate of some other gas, which we don't know, I'm going to call slow, is going to equal 3.16, and that we can do the square root, and we know the mass of helium. Okay, the mass of helium is about 4, but we don't know the mass of the other object. That's the other rare gas. We're trying to find what that is, so we're going to just call that M for the slow. So the mass of the slow on the top. We know that the ratio is 3.16. Okay, so how do we solve this? First we square both sides. 3.16 squared is 10, and then that gets rid of our square root, and that's the mass of the slow over 4, and then we can multiply by 4, so we get 40, and that equals the mass of the slow. And if you look at the periodic table, you'll see that the mass of argon is the rare gas, that is 40 grams per mole. So we know that the other gas must be argon. Okay, so that's all for diffusion and effusion. Now we're going to switch gears and talk about real gases. Okay, we've talked about ideal gases. We've done the ideal gas law. And we've talked about kinetic molecular theory, where we said the particle size is negligible, particles move in straight lines, and collisions are elastic. All right, but is this always true? Okay, it's not always true. Particle size being negligible. We talk about gases being ideal, and some gases are more ideal than others. Helium is a very small molecule, small atom, and so its particle size is small. But what if you're looking at a gaseous CH3, CH2, CH3? Okay, there's a lot of size there, and yet it's a gas. So the approximation that particle size is negligible is much better for helium than it is for this species, which is actually propane. How about particles moving in straight lines except for collisions? Well, that actually doesn't always happen either. If you have a gaseous water molecule sitting in space and another molecule, let's say it's sitting still, another water molecule is flying by, there's electrons and protons in these two molecules. There's some attraction. This second molecule flying by might be tempted to curve around. This oxygen might feel the pull of these more positive protons, and it might be attracted to them, so it might curve. So molecules aren't always going to move in straight lines, even when they don't collide. They're going to bend around each other due to attractions. And finally, the third assumption about kinetic molecular theory is that all collisions are elastic. Well, for the same reason it wasn't true here, they don't all move in straight lines, they're also not all elastic. Sometimes molecules, and let's represent them as just a ball, and another ball comes along and they're attracted, and they may be so attracted that they actually form a weak bond and they kind of stick to each other. So if that happens, then the collision's not elastic at all. Molecules actually do form weak bonds. So all these things contribute to the fact that kinetic molecular theory is an approximation, and it's true for ideal gases, but in real life, gases are not ideal. They might approach the ideal realm, but they aren't going to be ideal. So we have then the van der Waals equation, which is based on the ideal gas law, but it has room for these things not being exactly ideal. Okay, so you have a term here which has pressure in it. You have a term here that has volume in it, and it equals nRT. So here's your volume term, here's your pressure term. So it's kind of like the ideal gas law, PV equals nRT. But it's a little different because the pressure gets a correction due to the non-ideal behavior of the gases. So this is the pressure correction, and there's a pressure plus a correction term. Pressure correction is due to intermolecular forces. Okay, so intermolecular forces are basically what's going on up here. When you have things attracted to each other, there's a force between molecules. Then there's a volume correction. Which will be due to the fact that less volume is available when there's lots of particles. So if you pack a lot of particles into a space, the volume is actually going to be less than what you measured being. If you put them all in a container and there's a lot of them in there, they take up space, so the volume gets corrected. Okay, so the volume correction is due to less volume available when there's lots of particles. Okay, so it's essentially similar to the ideal gas law, but it has correction terms for the fact that real gases don't behave perfectly ideally. All right, and so they have these, they have N in the equation, and the N is the number of moles, and there's a V for volume, but then there's also these A's and B's. And we can tabulate values of A and B for various molecules. Okay, so for helium, A is 0.03 and B is 0.02, and that's not much use until we compare it to something. Okay, so helium's small. Let's compare it to a large noble gas. A is 4.2 and B is 0.05. Okay, so A is the pressure correction due to intermolecular forces, and larger molecules will have more forces between them, much larger. B is the correction due to the volume. So since xenon takes up more space than helium, it has a bigger correction B. Now let's compare it to one more thing, which is water. The value of A for water is 5.5, and the value of B is 0.03. Okay, so A, remember, was the correction due to intermolecular forces, and water, being a polar molecule, attracts to other water molecules quite strongly, so it has very large intermolecular forces. The volume correction, though, is actually smaller than for xenon. Xenon is a much bigger molecule than water because of the mass of oxygen isn't nearly as big as xenon, and of course hydrogen has very little mass at all. So the volume correction isn't nearly as, for xenon is the biggest of the three, but for intermolecular forces, water has the greatest correction. So it's just important to realize that while we use the ideal gas law a lot, there actually are corrections to that ideal gas law. It's not perfect. It works in certain limits, and those limits are when you have smaller particles, when there isn't a lot of traction between molecules because they're sparse, it's not a high pressure, and when the collisions are elastic, there's not a lot of forces between the molecules, which will also occur when there's not much pressure.